As we finish up this section on the Rice expression and how to do calculations with it, I thought I'd give you a taste for how it will be applied in the coming weeks as we look at real chemical systems that have particular value to us. In particular, I'm going to take a look at the Rice expression applied to an acid-base chemical reaction, one in which you want to know the pH of a solution. Now, as I show this to you, I show it to you understanding that in a couple of weeks, when I start working real acid-base problems, I'm never going to refer to the Rice expression again. From then on, I'm going to show you lots of fancy tricks for avoiding having to work very hard to get your answer. Yet, it's important as I leave this section on the Rice expression that you really do appreciate that this is the core, this is the root way that one goes about solving these problems. And you don't ever want to lose sight of that fact, because if you get too lost in the simple sorts of solutions that will come later, then you won't see the bigger picture of where it all came from. So I'm going to go ahead and work a problem here. I want to know what the proton concentration is for a 0.1 molar formic acid solution. Formic acid is ant bites. It's that sting you feel when you get bitten by an ant. Now, right here at this point, you can see two different concentrations. One of them is the starting concentration, and one of them is the equilibrium concentration. Well, this must be for some sort of equilibrium expression, and it is. It's formic acid right here dissociating to make protons and the base. Notice that this is that. And formic acid is HCOOH. So I'm going to set up the Rice expression. And as I do, I'm going to be sticking in the starting amount of formic acid, 0.1 molar. And evidently, I'm not putting anything else in the solution, because otherwise I'd tell you that I was going to do it. What is it that I want for the answer? I want this. I want that answer right there. Well, remember, the way you work this problem is by identifying everything in terms of a single variable. So let's let x be the amount of the proton. That must mean then that I am making x. I must be making an equal amount of the formate ion, because I'm making a one-to-one amount of each. And I must be subtracting an equal amount. Because the stoichiometry is 1 to 1 to 1, plus x and plus x forming, minus x going away. So this is the amount of formic acid going away. This is the amount of proton and formate that are formed. I have written my Rice expression so that everything is in terms of a single variable. Well, Ka, which is the equilibrium expression associated with this acid, is equal to the ratio of the proton concentration times the formate concentration, the stuff on the right, over the stuff on the left. And that's equal to x times x over 0.1 minus x. So Ka is equal to x squared over 0.1 minus x. Wow, that's a nice, simple little quadratic. A nice, simple little quadratic. Now, if I knew what Ka was, then I could go to town, solve this problem. Well, I happen to know what Ka is. Ka is 1 times 10 to the minus 4. I got that out of the back of a book. I can now solve this problem. How do you solve it? Once again, this is a problem like we've seen before. It's not a quartic, not even a cubic. It's a nice quadratic. And we know that if we wanted to, we could pull out our calculator and solve it. Heck, I could do my little iterative method like I did when I didn't have a calculator in the old days, where I'd stick in 1 and 0.1, oh, that didn't work. Let me stick in 0.01 and whatever, trying to get there. Or I could turn this into a quadratic equation solution. I could rearrange everything and put everything in terms of A and B and C to be able to solve it. But regardless, there is a way to solve this problem. And in fact, I'm going to show you a little trick one of the things that's coming is I'm going to teach you that that x there in the denominator, that 0.1 minus x there in the denominator, that x is really small, and I can ignore it mathematically. So that this problem is going to simplify to become 1 times 10 to the minus 4 times 0.1 is equal to x squared, or that x, which is my proton concentration, is equal to 10 to the minus 2.5 molar. Now, I don't expect you to understand what I did just then. That's what we're going to learn moving forward in the course. But the reason I show this to you here right now is because I want you to remember as you leave this particular lecture that when we start doing 105 million different acid-base reactions, this Rice expression here is the root for how that happened. The fact that they all look the same and we do them over and over again exactly the same, and that therefore I can skip all this part up here and jump right down to this answer here, is not really the point. The point is you need to know what this came from. It came from this Rice expression here. As I finish up then, do understand that for the next 6 or 7 weeks of material that's presented in lectures, no matter what kind of equilibria we're looking at, the key thing to understand is that you were starting with an initial concentration of material which is not at equilibrium, and you're wanting to learn what the final concentration is at equilibrium. And the easy way to navigate that is to set up a Rice expression, stick in the numbers that you know, look for the numbers that you don't know, and solve for it algebraically.